Hi guys, welcome back. This video is about adding vectors geometrically and algebraically. And sometimes people will call that analytically. Either one is fine, it's the same thing. And we're also going to talk about scalar multiplication. Having trouble with this marker. There we go, that's better. I'm going to talk about those both geometrically and algebraically or analytically as well. Also come up with a test for parallel vectors. We want to determine if two vectors are parallel. We'll be able to do this. And we want to find a unit vector in the direction of a given vector. It's very important in applications. All right. So adding vectors. One of my favorite professors, Larry Starhill, used to have this very whimsical way of teaching. He was fantastic. He used to talk about Mr. Geometry and Mrs. Algebra. I love this story. I love Larry's wonderful, whimsical personality. He'd say, let's talk about Mr. Geometry and Mrs. Algebra. He says, they're married. They have the perfect marriage. They always agree. He'd say, he's all about the big picture. She's all about the details. They come to exactly the same conclusions, but they come from different approaches. And I think Larry was right. Geometry and algebra are telling you the same story. They're just telling you the story from different perspectives. So that's basically what we're going to see when we're adding and subtracting vectors, when we're multiplying vectors by scalars. All of them can be thought of geometrically at first, and then algebraically or vice versa. And we'll see that they are giving you exactly the same result. It might be easier to take one direction than another based on the information that's given. But both of them are going to agree all the time. So they're just two different ways of saying the same thing. With that in mind, let's talk about adding vectors. In the last video, we talked about component form. So I'm going to do algebraically first, the algebraic approach. If I want to add vectors algebraically, it's actually very, very easy. Let's say that U has component form U1, U2, and V has component form V1, V2. Then you simply add component by component. The vector U plus V is written this way. It's defined to be U plus V. That always bothered me when I was a student. I'm literally taking the vector V, or U, and I'm adding the vector V, and I'm coming up with a new vector, and the way we notate that is this new vector U plus V. And it's just given this way. I'm going to take the X components of these two guys, I'm going to add them together. I'll have U1 plus V1 right here. And I'm going to take the Y components of these guys, I'm going to add them together. I have U2 plus V2. And that's it. Simple, easy breezy. So let's say, for example, I have U equals the vector 1, 3, and V equals the vector negative 4, 2. And I want to add those two together. I get a new vector U plus V. I'm just going to add component by component. I'll do 1 plus negative 4 and 3 plus 2. And so I get -3, 5. And that's our answer. Easy breezy. Now, the geometric approach seems a little bit more involved, but I actually think it makes a lot of sense. One of the easiest ways to think about it is in terms of displacement. This is just a memory device. It doesn't have to represent displacement, but it could represent displacement. Let's say I'm here in Tulsa, and I want to go to New York. I love New York. And one way that I could do that is I could take a flight that takes me to DC and then takes me to New York. So I could exhibit some displacement. I go from Tulsa to DC, and then DC to New York. Let's put that there so it's straight. That's one possibility. Or what's the equivalent displacement, guys? I bet you guessed it. I could go straight from Tulsa to New York. So this displacement plus this displacement equals this displacement. There should be a very clear arrowhead over here. I start where I started and I end up where I ended up. That's the geometric approach. Now let me do it in more abstract terms. So let's say if we're adding u and v, the first thing you're going to do is draw u. And let me just label this vector u over here. This place that we start, the initial point of u, we're going to call it the tail of u. And this place where we end up, the terminal point of u, is called the tip of u. So first you just draw u. And then, if you're adding v to that, you want to draw v with the tail of v at the tip of u. So let's say this is my vector v, maybe it looks like this. The tail of v is right there, and then this is the tip of v. Okay, there's u and v. If I want to add them together, then the sum, u plus v, starts at the tail of u and ends at the tip of v. I still think it's easier to think of it in terms of displacement. Start where you started, end up where you ended up. You're just going to go that way. That's the vector u plus v. Any questions about that? I know it's a video. That's what I'd say in class. Okay, so that's u plus v equals that. We can also see from this little triangle that u plus v and v plus u are going to give you exactly the same thing. Watch this. If I wanted, instead of starting here at the tail of u, and then going this way and drawing u first and then adding v, I could draw v first and then add u. So let's say I started at this same point and I added v first. Now v has that magnitude and direction. I can start it at any location that I want. So I'm going to start it down here. So that's v. So there's tail of v, now tip of v. Now I'm going to draw u with its tail at the tip of v. This is called adding tip to tail. I'll write that down in a second. Now draw u over here. Same vector, just over here. Same magnitude, the length is the same, the direction is the same. This is u. And v plus u starts where I started and ends up where I ended up. Sometimes you'll see this called the triangle rule, when it's just this half. Or you'll see it called the parallelogram rule when it shows both. U plus V and V plus U are the same. But you see, if you've got U and V as adjacent sides in this parallelogram, the sum U plus V is like this. Now it's very important that it fits this pattern. We have to draw it this way, going from here to here and then here to here. If those arrowheads were at the same location, or if both tails were at the same location like they are here, like U plus V is not that diagonal, it's only this one. So you have to be very careful. So we draw U, start where we ended up, draw V, start where we started, end up where we ended up, that's U plus V. And I think thinking in terms of displacement is very helpful. Again, this is called adding tip to tail. Now, obviously, this is much easier. This is a little bit more to remember. It's not too bad if you remember this displacement. But you might say to yourself, I'm not 100% sure, Miss Townsend, that if I do this, it's exactly the same as doing this. It turns out that it is. Let me show you that these two approaches are equivalent. Larry Starhill was right. The algebraic approach and the geometric approach are just two different ways of saying exactly the same thing. Let's draw it and see. So let's say I want to add the vectors u with components u1 and u2 and v with components v1 and v2 together. I'm going to do it geometrically. I'm going to show you in my picture. So let's say u looks like this. Well, u1 is the number of units I go in the x direction to get here. So this is u1. And u2 is the number of units I go in the y direction to get there. So this tick mark would be u2. Or if I want to label side lengths, this is u1. And this side length here is u2. Or if I prefer, I could draw it over here so it's sort of out of the way, u2. That's the vector u. Now if I'm adding tip to tail, I would start here and I would draw the vector v. Maybe this is my vector v. This can also be broken up into components. I draw a line segment or a dotted line that's parallel to the x-axis and another one that's parallel to the y-axis. It's giving me this little triangle. That's very obvious what my components are. By definition, the x component of v is v1. So I've got v1 there, and the y component of v is v2. Okay, well, u plus v, according to our tip to tail rule, starts where we started, it ends up where we ended up. Just like I'm flying from Tulsa to New York. That's u plus v, new vector. Question is, what are the components of that? Geometrically, let's look at the picture. I've got this is u1 and this is v1. So what does this tick mark have to be? That was 3 and that was 2. I just do 3 plus 2 and that'd be 5, right? This has got to be u1 plus v1. That's the length of this component of this purple vector. That's u1, whoops, u1 plus v1. And the y component, well, that's u2 plus v2. So if I'm adding geometrically, I do u plus v equals u plus v. If I'm adding analytically or algebraically, I do u1 plus v1, it's u1 plus v1, and then u2 plus v2, u2 plus v2. When I'm adding algebraically, that's my result. Add component by component. So we can see from this picture, oops, that should be u plus v equals that. We get exactly the same thing either way. So the algebraic approach and the geometric approach are equivalent. That's exciting. It's a good thing, a very good thing. We wouldn't want them to be inconsistent with each other. That'd be very bad. Label my y-axis and my x-axis. All right, so that's adding vectors algebraically. Let's talk about scalar multiplication. First, let's talk about it algebraically, or analytically, whichever you'd prefer. If my vector u has components u1 and u2, and c is a real number, this little e means is an element of, it's actually kind of an epsilon, I think. Or you might say it's this C is in this set over here, and that set is the set of real numbers. The R with the double bars is the reals. So if U equals this, and C is just a real number, then C times U is probably exactly what you expect. You just multiply that scalar through. It's like distribution. Do C times U1, that's the new x component, and C times U2, that's the new y component. So this is easy breezy. U is the vector, 2, -3. 5 times U is, I take the vector 2, -3, and I multiply each component by 5. Multiply the 2 by the 5 and the -3 by the 5. And that's going to give me a 10 and a -15. Super easy. All right. That's adding algebraically. Multiplying by a scalar algebraically. If I want to do the same thing geometrically, or if I want to interpret the same idea geometrically, let's talk about it. If C is positive, C times U points in the same direction as U. So they have the same slope. And is C times as long. So if this is my vector U, 2u, it's going to be, that's 1u, that's 2u. It's going to be the vector that goes from there to there like that. 3u. I'm not sure if I'm getting the length exactly right because I'm drawing this by hand, but you get the idea. That's 1u, that's 2u, that's 3u. And just multiply the vector by 2. It's twice as long. Multiply it by 3. It's 3 times as long. Multiply it by a half. Half as long. Now, if I multiply by a constant that's negative, then CU points in the opposite direction. And its absolute value of C times as long. The negative is what's flipping it. It's moving it in the opposite direction. And then the magnitude of C, or the absolute value of C, that's changing its length. So if that's my U, negative U, and try to draw it exactly the same, but in the opposite direction, that's that right there. And negative 1/2 U, point in the opposite direction and be half as long. Negative 2u, I'm trying to do it, it's really hard to do. Might look like that. Twice as long, but in the opposite direction. It's like we added 180 degrees or pi radians to our angle. Okay. So you might say to yourself, Miss Townsend, I'm not 100% sure that I believe that multiplying those components by C is the same as changing the length. It's actually very easy to see. Let me show you. I'm going to do a very simple example. I'm going to try to make my tick marks as evenly spaced as possible because it'll be clearer. The better the grid I have. All right, so let's say this is my vector u. I'm just going to use the vector 1, 1. Then 2u, algebraically, I multiply both of these guys by 2 and I get 2, 2. So I go out to this point, 2, 2. Don't those point in exactly the same direction, only this one is twice as long? Isn't that the same thing? Or how about this? Negative 3u. That's going to be negative 3, negative 3. Take the 1, multiply it by negative 3, take the 1, multiply it by negative 3, and I get that. Trying to make everything nice, nice. Negative 1, negative 2, negative 3. Isn't that in the opposite direction from you, but 3 times as long? Well, it should be. My grid isn't exactly perfect, but you get the idea. In general, if this is the vector u, where this is u1, this distance here is u1, and this distance here is u2, if I multiply it by a constant c, c times u looks like this, and this component is c times u1, and this component is c times u2. It's a little bit difficult to see in this case, but I think it's a little bit more obvious here when we've got the concrete example. All right. Notice all these vectors are parallel to each other. My picture over here, when I drew them apart from each other so they had different initial points, all of these guys are parallel to each other. I take a vector and I multiply it by a constant, it's parallel. Or if I take a vector and multiply it by a constant, and we start at the same point, then they start to overlap if they're pointing in the same direction. If they're pointing in opposite directions, they're just on the same line, they're just going the other way. So we've got a test for parallel vectors now. The vector u is parallel to the vector v if and only if, not a spelling error, it's just mathematician's abbreviation for if and only if, u is a constant times v. That just means u is a rescaled version of v. I've just changed the length, or possibly the length and the direction. If they're constant multiples of each other, they're parallel. So here's an example. Oops, the vector 1, 2, 3. Is that parallel to 2, 4, 6? I hope you said yes. No, Miss Townsend, that's so obvious. If I just multiply that one by 2, I get that one. You're right. 2 times that one is that one. That means 1, 2, 3 is parallel to 2, 4, 6. What about these two guys? Are those two parallel? Call this one u and this one v. I hope you said no. They're not parallel. Okay, say, how do you know, Miss Townsend? Well, if I want to go from 1, 2, 3 to -3, -6, 9, I have to multiply this x component by a -3. So if these guys are multiples of each other, the only way that would work is if u times -3 was v. So let's check out -3u. You probably already see it coming. Distribute the negative. You say, oh, they're the same. Oh, no, they're not. Watch that sign. Those are not the same. So here, u is not parallel to v, because u is not a constant times v. If it was a constant times v, it would have to be -3 times u. Or excuse me, v is not a constant times u. V would have to be -3 times u for it to work, for those first two components to be right. And it does work for the first, or for the first component of u and the first component of v to be right. And it does work for the first two components here, but it doesn't work for the third component. And I accidentally started talking about vectors in 3D, but we're going to do that. We're going to do that very shortly. So if the 3D version of the vector bothers you, try not to worry. This is an x component and a y component. In the next video, we're going to talk about z components. All right, so vectors are parallel if and only if they're constant multiples of each other. Okay, so one last thing. It's often important in physics classes to find a unit vector in the direction of a given vector. Let's say you've got a cable. It starts here and it ends up here. The cable looks like this. Maybe this is the point x equals, just going to add a coordinate system. Maybe this is x equals 1, y equals 1, and this is, I don't know, 52, 18, or something like that. Maybe there's a cable that, based on our arbitrary coordinate system, it starts there and it ends up there. If I want to know the force in this cable, the length of the cable itself is not going to tell me anything about the force in the cable or the tension in the cable. But the direction of the cable, that's really important. And the direction is usually specified by a unit vector that goes in the direction from here to here or vice versa. So we would add some arbitrary vector. Let's say that's P and that's Q. Add our own labels, and I want to start here and end up here. If I want a unit vector in the direction of PQ, the first thing I need to do is find PQ. This is obviously not to scale. I think I switched those in my head. I think I'm going to switch them right now. I think that 18 and that 52. That's what I meant. Okay. Got the vector PQ. How many units do I go in the x direction to get from 1, 1 to 18, 52? To go from 1 to 18, I go 17 units in the x direction. You can think of it that way. Or you can just use the formula, terminal minus initial, 18 minus 1, 17. Terminal minus initial, 52 minus 1 is 51. All right. Or you can say, what's that distance from there to there? Well, if that's 1 and that's 52, that's got to be 51. Right. That's the vector PQ. If I want the unit vector in that direction, the vector that's exactly 1 unit long that goes in that direction, well, it's actually pretty easy. First, I find the length of this vector. I don't know what it is. Remember how we find length? We take the components, square them, add them, and take the square root. I would probably use a calculator for this. And I'm reaching in my purse. I'm going to. (17 squared plus 51 squared). Take the square root of that. I love this Casio calculator. It's beautiful. Oops, I just wrote 15, but I meant 17. I was using the wrong color. So I've got 17 times the square root of 10. That's the length of P to Q. If I want a decimal approximation, just because I'm looking at a physical application, it's about 53.76 units. Maybe it's feet, maybe it's meters, I don't know. But that's how long this is. This is about 54 units long. If I want it to be 1 unit long, if I want the little vector down here, it only goes 1 unit in that direction. I just take this and I divide it by its length. So the unit vector in that direction is denoted by U, and we always put hats on it, U hat. We're going to use hats anytime we have a unit vector, just to make it very clear that it's only 1 unit long. The hat means it's tiny. Let's say they're cute or something. Unit vectors wear hats. So I take PQ, I divide by the length of PQ. I'm dividing, divide component by component, just like when you're multiplying by a scalar. We end up with 17 over 17 times the square root of 10. Those 17s reduce. And 51 over 17 times the square root of 10. I don't think 51 is divisible by 17. Oh, it is 3. So I get 1 over square root of 10 and 3 over root 10. That is the unit vector, or that is the vector that points in this direction that is exactly 1 unit long. In general, if I want the unit vector in the direction of V, I take V, maybe it's 5 units long, then I divide it by 5. Well, that's not in general. And then it would be 1 unit long. So I take V and I divide it by its length. Sorry about that. There we go. That's the unit vector in the direction of V. Whatever length it was, if it was 5 units long and I divide it by 5, now it's 1 unit long. You don't believe me? Take these, square them, and add them and take the square root. I bet you get 1. That squared is 1/10. That squared is 9/10. What's 1/10 plus 9/10? That's 1. Take the square root of 1, you still get 1. So that is definitely a unit vector, and it points in this direction. And again, we're seeing this a lot in applications, physics, applications especially, usually problems involving forces, tensions, things like that.